So back in 1995, JavaScript was created by Brendan Eich, right? And he did it in 10 days, which is pretty crazy. You know, that it's what most of the web is built of now. So JavaScript is 18 years old now, so it's like legal to drink in some countries. I saw someone on Twitter saying that they think they've seen JavaScript drunk many years ago. A lot of the time, quite like that. But in 2010, another team set about making a new language, and from what we know now of the web, we know how the whole web's put together and the kind of tools we need. And that team is the Dart team. And here to talk about it, big warm welcome to Seth Ladd and Kasper Lund.
Okay, thanks, Jake. So we won't be playing the Kenny G. We don't want you guys to fall asleep. This is Dart for the modern web developer. My name is Seth Ladd. I'm a developer advocate with the Chrome and Dart team.
And I'm Kasper Lund. I'm an engineer here at Google. I work as a tech lead on the Dart platform. And before I ventured into Dart territory, I spent a lot of years on optimizing V8 and the optimizing compiler in there.
OK, so many of you know Dart as a language. And sure, it's a structured, scalable, familiar language. But it's also, I like to think of it as a batteries-included platform. There's a great core set of libraries, things like collections, things like asynchronous programming, futures, streams, things like numbers, booleans, dates, times. We also ship a collection of productive tools, a Dart editor, an analyzer to give you warnings and errors, a package manager we affectionately call pub because you play darts in a pub. We also ship a virtual machine, which runs Dart code natively. You can run that VM on the command line or on the server, and you can also embed it in client browsers. But probably most importantly, we ship a compiler to JavaScript. So the Dart code you see here today and the Dart apps that you'll be writing, you can compile that down to essentially ECMAScript 5 and run it across modern browsers, desktop, and laptop. You might have heard recently we launched Dart 1.0. It's a big milestone for us, hopefully exciting for you guys. The big point of this really, yeah, thank you. OK. The journey starts here, really, for us.
Definitely, yeah.
The big point here, the big takeaway is it's now stability you can count on. We've been open source since about October 2011 and gotten tons of feedback from internal developers, external developers, hackathons, code labs. And we've collected that all and launched what is now a stable language, stable core libraries for you to build production apps on. So now is the right time to try it. OK, so when I said you can use Dart today, I think I actually mean you can use Dart like in the next hour. So we're going to do a lightning tour of the syntax, structure, and semantics to show you how familiar and easy it is to get started. So Dart, by design, is very easy to learn. We have semicolons, we have curly braces. In fact, we got a little flack when we first launched Dart. People were like, why don't you make the next big Haskell? And we're like, we want more than 5 users. And so we wanted to make sure that you guys can totally understand this code. We've run hackathons and code labs. People get it. So familiar, classes. But just because it's a familiar language you can dive into in about an hour doesn't mean we can't take this opportunity to introduce new features. For instance, with constructors. What do we always do in constructors? This.x equals x, this.y equals y. This is getting boring. So Dart says, hey, if the name of the field is the same as the constructor parameter, just say this.strength in this case, and that will desugar to this.strength equals strength. Just those nice additions to make this feel more terse, more scripty. Speaking of scripty, Dart has operator overriding, so plus, minus, et cetera. That's in this language. We also have named optional parameters. Again, it's a structured language. It may look like the structured language you've been using, but it has those features that allow you to have a terse programming experience that you might be more familiar with in scripting languages. In fact, this case here, hands is an optional parameter, but also has a default value of 1. So say more without typing more. We also support one-line functions. This is critical. There's a lot of callbacks going on in web programming, and a lot of times you want to do really small inline function literals. We support that with the fat arrow syntax. And we also have string interpolation, making it very easy and quick to create strings, just $, variable, or expression. And it's right there. It's a lot easier than doing string builders or string concatenation. OK. So Dart is its own language. It's not just a syntax that masks another syntax. We have our own clean semantics. So we want to turn more of these what moments, which I'm not even sure what's going on here, into the totally awesome atomic dinosaur nuclear rocks. We want you to have more on the right, less on the left. OK, so some examples of the cleaned up semantics give you a more logical programming experience. In Dart, only true is truthy. There you go. Now you know the truthy rules. Good job. OK. There is no undefined, only null. Yes, totally cleaned up. OK. No type coercion with things like double equals and plus. So when you try to do something funky, we're going to tell you. OK, pop quiz time. Here's a string, hello, we call dot missing, which obviously does not exist on string. What would you want to happen at this point?
Undefined?
I don't want undefined. I want to be told that there's no missing method on string. And sure enough, at runtime, when you hit code like this, the program tells you with a very clean error. So a much more logical programming experience. OK, if you were to compare hello, which is a string, is it greater than 1? I think this returns false, but actually I'm not really sure why. So what would you want this to happen, right? You want an error. You want to be, hey, man, string does not have an instance method greater than. You get told at runtime exactly where the problem happened. Much more logical programming experience. OK, variable scope. This one's a little bit longer, so take a look at this. We have a main function. If true, there's foo, and then print foo, but there's also a top-level foo. So the question I have for you is, when I run this, what will it print?
Any takers?
Okay. It's a 50-50 chance. Top level, right. This prints top level, and Dart, no variable hoisting. It's a totally logical lexical scope, lexical analysis of what's going on. If you hand most developers this code, they will be able to understand what's going on here. Speaking of lexical scope, even this is lexically scoped in Dart. This is one of the things that totally tripped me up earlier. Here's a class, awesome button, and in its constructor, you set up a click handler. And when the button is clicked, call this.atomic dinosaur rock. Well, what is this at this point? The lexically scoped this. That is an instance of awesome button. You give most people this code, and they will tell you what method this is calling on, which is, I think, a pretty big improvement. OK, so that's a little bit on the semantics and a little bit on the syntax. But Dart is also designed to scale from just a couple lines of code. You could certainly write a 10-line Dart script and have it look very scripty. But you can scale all the way up to millions of lines of code. Now, we saw functions. We saw classes. We have mix-ins. We have interfaces. I want to talk about libraries, which is a nice piece to help you modularize your code. Dart libraries are very flexible. You simply define a file as a library. You can import libraries from the core SDK. You can import libraries from other people or other files. And then you can define any number of top-level constructs in a library. So no more like one public class per file thing if you come from Java. So in this case, 2 classes and even a top-level function. In Dart, you don't have to wrap everything in a class if you don't want to. So nice, scalable structure for you to grow. So hopefully you guys saw that this is a language you can start using right away. But of course, we use Dart to get onto the web. And to get on the web, you have to compile Dart to JavaScript. And to do that, and to show you how it works, I'll turn it over to Kasper to tell you all about Dart to JS.
Oh, thank you, Seth. So finally, now I can say something. It's wonderful. So I'm going to tell you a little bit about how we compile to efficient JavaScript. It's very, very important to us to make sure that Dart runs really well on all modern browsers. So we put a lot of effort into that area. So our goals are fairly simple. We want to generate small code. We want to generate fast code. And we want to make sure that we retain the nice, clean, proper Dart semantics while doing so. So simple goals is a good starting point. But to do this and to do it efficiently, we need a real optimizing compiler, something that doesn't just do like a one-to-one translation in a simple way. We actually need a lot of the neat modern compiler techniques that we've learned to love from other, say, more involved projects like V8. So we need function inlining. We need loop invariant code motion. We need global value numbering. We need a lot of these things: type propagation, redundant load elimination, dead code elimination, and much, much more. So we need a lot of things in this compiler. We want to do a good job in optimizing your code so you don't have to worry about it. So let's take a look at a very simple Dart method just to give you an impression of what we actually translate the code to. Here's a main method that allocates a few points, and then we compute the distance between these points. Very simple code. Luckily, a simple Dart method actually compiles to relatively simple JavaScript too. So you will allocate points the same way as you would expect it to. The only real difference here is that when you call the distance to method, we actually encode the arity, the number of parameters passed, in the method name. Now, why do we do that? The reason why we do that is because in JavaScript, we're allowed to pass any number of arguments. Too few or too many, it doesn't really matter. But usually it leads to weird and surprising behavior at runtime if you do that. So we want to be a little bit stricter there. So to live by Dart's proper semantics rules there, we actually have to check that you're calling with the right number of parameters. And the fastest way of doing that is just encoding it in the method name. If you call with too many parameters, you'll get an error that that method doesn't exist. So when you have large applications, you need some sort of tool to make sure that you're not actually shipping too much code to your clients. In particular, in a setup where you have a nice, rich set of core libraries and a nice set of third-party libraries you can include, you want to make sure that whatever you ship to your clients is only the needed bits, not all the other stuff. To do that, we have an implementation of an algorithm called tree shaking in the compiler. It works a little something like this. If you have an application that has a main method and perhaps a few other methods close by, foo and baz, but it's only calling the foo method, and maybe the foo method in return calls code pulled in from another library, the bar method on the right. That library might actually have unused parts too, like the boo function here. We want the Dart.js compiler to actually take this set of methods, like the transitive closure of everything that you have available to you, and shake it real good and get all the stuff that you're actually not using out of the system. It's a process called tree shaking. We do that, and the result is a lot smaller. It only contains main, foo, and bar, the needed parts. So to implement this in the compiler, we actually go through a few steps. First, we read all your Dart sources. We don't actually parse them fully. We don't look into all the methods. We just look at the structure of your code, find all the imports, look at the libraries that you depend on, and read those in too. When we have everything read in that way and we know the structure of your code, we can actually start doing this first level of tree shaking. We have two levels. This is the first one, and this actually is what we call the resolution tree shaking. And resolution is the process of not really compiling code, but just trying to figure out what you're referring to at certain points in the code. So it actually starts by looking at the main function and look at what kind of classes or instances of which classes you allocate in there and which other methods you're calling. All those methods need to go into a queue so we can process them, parse them, get them resolved. And you just keep doing that until nothing new is added to the queue, and then you're done. It's relatively simple to do this, and it gives us a good approximation of like cutting down everything, but only based on method names. We can do a little bit better. So once we're done with that, we actually start the process all over again in the compilation queue. And this is where we actually will start looking at what you really put inside your methods and do data flow analysis. And we will track how types flow through that code. And that gives us more information about what you're actually needing to emit. And we do the last level of the tree shaking at that point. The end result is that we do a really good job in making sure that things that you really don't need are not pulled into your application. Finally, we actually emit the code to a single JS file, so you can run it in your browser. Fairly simple stuff.
I love this because this is the tools helping me. I mean, I don't need to be crafting my application. I just let the tool analyze my program, take care of it.
That's the way it should be. Mm-hmm. So let's take a look at how this actually works in practice. Just to give you a feel for how Dart.js does its magic, I'm going to dive into a well-known algorithm. It's a constraint-solving algorithm. The reason why I'm choosing this one, it's a well-understood piece of code. It's been used to benchmark lots of different language implementations over the years. It's actually part of the Octane benchmark Linus mentioned this morning. So it's a well-known piece of code. It is structured. It has inheritance and classes and everything we need to actually do a good job in making your code run fast. So let's take a look at it. Delta Blue is a constraint solver. What does that mean? Well, basically, it's a fairly abstract thing that works on constraints on variables. Constraints can be like one-way or two-way. They're binary or unary constraints of different kinds. And they can be used to, for instance, model the constraints involved in laying out something on your screen. I'm pretty sure that some of the things you just heard about from Eric actually uses constraints and things like that internally when building layouts. So Delta Blue is an implementation of such a beast. It uses constraints, and there's a nice hierarchy of them with unary and binary constraints and variables. Let me show you a piece of code from this thing to make it a little bit more concrete. This is a function from the Delta Blue algorithm. It's fairly simple. You don't have to understand all the details here, but just note that the way it works here is that you take a variable v and you try to figure out all the constraints that actually consume that variable and put them in a list that is also passed in as a parameter. Hopefully, this code is reasonably readable to you. It's Dart code, and to me, this looks like what I would expect.
Kind of representative of code a lot of us would write.
Yeah. So in Dart, we have an optional static type system. So you do not have to write the types if you really don't want to. Sometimes it's nice to be able to document what a parameter means, which is why I didn't done it here. But it's important to us to make it clear that the types that you put in are not actually used for optimization purposes, because we don't really know if you want to type them in, so we don't want to force you into typing them in the places where you don't want to. So I can go ahead and remove them.
And they might also be incorrect.
They could be incorrect, yeah. Anyway, I've gone ahead and removed the types. The semantics of this algorithm is exactly the same, no differences at all. It's just a little bit shorter and maybe a little bit harder to understand. But anyway, the code is there. It's the same thing. And this is what we're going to try to optimize. So first attempt at actually compiling this code to JavaScript is somewhat large. So this is the unoptimized version of the method you just saw. It compiled to, I don't know, 500 and something characters. It's a little bit too long. I'm not even sure you can read it on the back of the hall here, but it works. It has the right semantics. Everything works as specified, and it runs reasonably well. But it's, I hope you agree, it's simply not good enough. Like, we want to do a lot better. So let's try to dive into how we actually do better than just this blob of code. Even though the semantics is really important to us, we also really care about performance. So what makes this big? Well, this is just one of the examples of why this code is a little bit bigger than what we'd like. So as Seth mentioned, we have strict semantics about what you can compare to numbers, for instance. So we don't want to run into issues when you end up emitting JavaScript code that just ends up comparing numbers and strings, for instance, because we don't really want to rely on that behavior. So in this case, we're reading, see if I can get this to progress. There we go. So we're reading the length of something that probably is an array, but we're not quite sure. So we don't know that the length is actually a number. So before we continue to actually compare this length against a real number, we have to make sure that it actually is a number. So we insert an explicit check in the code that makes sure that we don't end up relying on this somewhat surprising behavior of JavaScript where you can compare numbers against strings and get some result out. So this adds code, more checks. So our challenge is fairly simple. We want to have clean semantics, unsurprising behavior, but we do not really want those extra checks when we're compiling to JavaScript. So how can we go about doing that? The trick is right behind me, global optimizations. So we really need to do better, and we need to do more aggressive optimizations in the code to make it end up being very fast and very good. So let's look at that. First up, Dart is structured. It has classes, it has methods, it has good structure. We can actually do whole program analysis. So when we compile the program, we can look at every single bit in it, and we can actually understand what's going on. That's a huge win for us. This allows us to actually do code navigation and great refactoring tools, but maybe even more and more dear to my heart is that we can also do global compile time optimizations. So we can actually analyze your code, understand the dependencies between things, maybe to a certain extent better than what you actually care to do yourself as a developer, and then we can optimize based on that. It's pretty powerful. One of the things that we do, and one of the things that really work well for something like Delta Blue and for most applications in general, is that we infer types. We compute what types we actually will see at runtime at different points in the code. And the way that works is, here's a simple example of how that works. Main function calls foo, that calls bar, that calls foo again, basically. So a bunch of functions calling each other. So how do we infer types for the parameters of these things? How do we get the compiler more information? Well, we start by looking at main. So it's very simple. And by analyzing main, we can see that foo is actually called with an integer parameter. OK, so far so good. So we analyze foo under the assumption that this is called with an integer parameter. Do we learn something from that? Sure. Bar is apparently also called with an integer parameter. So far so good. We can continue this game a little bit. So we end up in bar, and we realize that if bar is called with an integer parameter, then it ends up calling foo with a string interpolated version of that parameter, which is a string. So foo is now called with a string too. So we have to go back and iterate. So foo is now apparently also called with a string. That means bar is called with a string too. And finally, inside the bar method, we realize that that means that print is called with a string. So far so good. All in all, the compiler can actually conclude that x and y are both either integers or strings. This is a very, very simple example, but that actually works really well in practice for large apps too. So let's look at Delta Blue and see how that actually works there. It's pretty simple. So there are a couple of things here we want to infer types for. For instance, the two parameters, like v and call. And the inferer actually does that by looking at all the call sites that call at constraints consuming 2. And we actually learn that v is either null or a variable. And that call cannot be null. It always is a JavaScript array containing only subclasses of the class constraint. That's pretty powerful. So that's good to know for us. The rest of the method here can also be analyzed, and we can learn something about all these constructs in there. So we can actually get a pretty full picture of what the types in here are. So I've just listed them here. You don't have to look at all the details, but this is very good information for our compiler to have.
And it does this without running the program, just statically analyze, just looking at the program.
This is global analysis at compile time. So let's make this play to our advantage. So here's the code again without type inferencing, 526 characters. So first thing up, like we know v is either null or a variable, so we can do a little bit better than just calling this getter on it. So we can actually see that it always has a property determined by, we just fetch it, simple stuff. There are other things that we can win even more by recognizing. For instance, v, the variable.constraints. Since v is a variable, the constraints in there is always an array of constraints. So we don't have to go through this like calling a length getter and calling an index operator. We can just do like the real JavaScript way. Just fetch the length and just index into the array. Simple stuff. Even better, we know that v.constraints that length is actually an integer. So this whole notion of checking whether or not it's a number goes away. So that is a helpful thing. It's starting to improve. Now the condition that we have in the loop is turning simpler. We can change the while loop into a for loop. And at that point, we're already down to 33% smaller than the original code I showed you. We have more to go, but it's pretty simple stuff. Call is an array, so this calling add on it in a weird way is not really necessary. So we can just use the JavaScript push method, do that for you. It looks good. Even further, the T1 is initialized in a simple way, so that can just move into the for loop. And we're down to 41% smaller than the original JS output. It's starting to get there. C is known to be a subclass of constraint, and it cannot be null. We've inferred that. So this whole notion of checking whether or not C is null before doing a comparison, this is necessary because of null and undefined in JavaScript, by the way. We don't have to worry about that because at least C cannot be null. So we can simplify the code. It's a good thing. Finally, we know that calling is satisfied on C actually always returns a Boolean. And true is the only truthy value in Dart, so usually we have to compare against true before we branch on it. But because a Boolean is always either true or false, it's just fine. We can get rid of that last thing. And there you have it, an optimized version of this method that runs fast. It's much smaller, but it still has exactly the same semantics. It's just we've proven that we didn't need some of these checks. So what does that do to performance? Well, here's the graph of that over time. So the top line is the native Dart VM running the Delta Blue algorithm. So you see that's the best performance we have, and it really comes from the fact that Dart is designed from the get-go to be an efficient language, so we have a very good implementation of that. The next two lines might be more interesting in this context. The yellowish line is actually a V8 running a handwritten version of the Delta Blue benchmark. This is the Octane version of the Delta Blue benchmark that you might have seen in other places. As you can see, V8 improves on that over time slowly, and that's a very good thing for the entire web. Maybe more interesting to me, at least, is that the Dart.js generated code has improved a lot on this benchmark. It's still the same V8 that runs it. It's just that the code we generate is actually a little bit faster than the handwritten version. How could that be? Well, basically, we do optimization that you probably don't want to do by hand. Because we know the entire structure of your app, we can do some inlining for you and some code motion and things like that for your loops that you probably don't care to do by hand. So it's a little bit faster. In general, what we see is that we're very close to handwritten JavaScript performance on everything. So there are cases where we're faster, and of course there are cases where we're a little bit slower. So anyway, the performance looks really promising, and it's nice to be able to write in a very clean language and get good performance. So let's take a look at how you actually go about using this Dart thing in a real setting.
Yeah, thanks, Kasper. So that's Dart.js. A little bit about the workflow. How and when do you apply that? Compiling JavaScript, of course, is great, but I don't want to do that every time. I want those quick iterations that the web is known for. So what does it look like? Well, we have a build of Chromium with the Dart virtual machine embedded in it. We affectionately call it Dartium. And that's where you spend most of your time. Those are your quick edit reload cycles. So let's look at what that feels like. Here's a build of Dart Editor. You don't have to use Dart Editor, but it does ship with the project. It's a stripped-down version of Eclipse. In fact, I like to show this. I showed this screen to somebody, and they're like, oh, you have a bug? You're missing like 78 more preferences in there? Like, no, actually, we took those out. So it's optimized for writing Dart code. Probably the best way to get started is let's just create a sample app. So luckily, Eric showed us Polymer before. Dart has been porting Polymer, Polymer.dart. So we're totally in bed with this web components thing. We think it's the bee's knees. Here is a sample application. You get all the skeleton for you. You've got the HTML. You've got the custom elements, the CSS. So let's just run this here to see what it's like. It's very simple here, but we're going to run it in Dartium. See, it pops right up. No compiles time needed. Click me, OK, button, click counter. OK, cool. So it gives you just the core to get started with. Let's look a little bit how this application is written. Hopefully you can see this. So the Polymer element looks pretty much like what Eric was showing you earlier. So the HTML aspects of building highly declarative apps with Dart are very similar to the JavaScript side. The difference, though, instead of implementing the custom element with JavaScript, you can implement it with Dart. Dart has classes, so it makes a ton of sense to be able to say one class for one custom element. So this is cool. And I'll show you a couple other features because Dart is structured, and this editor gives you some nice productivity benefits. Let's say I want to add a reset count and then a method here. OK. Code completion. Because we can statically analyze your program, we know what you can call right here. And it's real time. So that's pretty awesome. And also go in for the local stuff as well. OK, that's pretty cool. Now, the other neat thing about a statically analyzable language is it can understand your program. So let's look at this field count. Notice how it only highlights the uses of that field. It's not doing a string search and replace here. So it leaves out some of the other counts, even though obviously it's the same string. So we can do, we can rename. We can say my count. And it only renames the actual usages of that field. Again, the power of a statically analyzable language. I'm going to undo that. I'm scared of bugs. OK, cool. Once you're in an editor and you have an actual virtual machine, you can set breakpoints. So let's go back. We set a breakpoint there. We're going to rerun the app. And if I click the button and it all works, yes, OK, great. So it jumps back to the editor, and you're in a familiar editing environment with full breakpoints. You can inspect. This is really cool. I can jump in here. I want to inspect this instance. I don't know if you guys can see this, actually. Trust me, that says count, and then 5. So it's a live object inspector. So that's really cool. So let's move on. This app was kind of neat, but it's also kind of boring. So I think we can do a little bit better. In fact, that gray button, I want to make fancier. So this is where our package management system comes in. And our package management system pub, let's see if we can go here. Has over 500 packages in it already from our open source community, everything from server-side stuff to client-side stuff to game, crypto, you name it. Here, look at this. Fancy button. OK, so our pub package management system also has custom elements in it. So if you like web components, you want to reuse them, the package management system is a great way to do that. So let's make our button a little fancy. Let's load up the pubspec.yaml file. This defines my application and its dependencies. And certainly, I depend on Polymer. Let's depend on fancy button. OK, great. So now the editor's kicking off pub. He's going to go download it and install it and make sure it all works for my app. I'm a little impatient, so I'm going to go over here and show you what that looks like. We're going to go into click counter. And just like regular web components and HTML imports, you can import the definition of fancy button. You can say that this button is a fancy button. Now, this is all backed by Dart. It's a real web component, and it came to us from that package management system. Let's see if I indeed made it a little fancier. So run in Dartium, and yes, awesome. OK, pink. OK. So it's a nice just demonstration of how you can use a package management system and reuse code. Finally, we need to get this out into the wild. It's one thing to iterate very quickly in Dartium, but it's another thing to be able to find my original slides. Beep. OK. Do your final testing in production browsers like Firefox and stable Chrome. And this is where our pub build system comes in. So iterate very fast with Dartium in the editor, and then run a nice build process. Now, more and more web developers are moving to a build process. It does really nice optimizations. For one, ours runs Dart2JS. So you saw some of the nice optimizations it can actually do with your code. Tree shaking, it can minify your app. If it totally knows your entire application, it can do a really smart job of minification. It can also do concatenation. It can take all your dependencies, all your custom elements, and jam them all together into one single file, making the deployment and performance very, very good. In fact, in this particular example, I mean, you saw we had a lot of dependencies, third-party stuff, custom libraries, core libraries. This app compiles down and gzips down to smaller than some CSS frameworks you guys use. So I think it's kind of cool. And just to show you that that all works, here we have it in Firefox. And it's the same. This is Dart compiled to JavaScript using web components deployable to a production browser today. This stuff is real, and you can use it. OK. And then when you're finally ready to go, you have a nice build directory, which has just the assets, just those minified files, in a very nice directory you could pick up and put onto the web. All that concatenation, all the minification done for you.
Nice and simple.
Nice and simple. So how do you get started? Well, we relaunched the website, and we have a really nice code lab. Takes under an hour, walks you through 0 to 60. You get to build a really cool pirate name badge generator, so a really nice way to try Dart, built for if you don't know anything about Dart. And I want to leave you with a reminder that Dart 1.0 is for the modern web. It's a platform you can use today. It's easy to get started. Go to dartlang.org with APIs, code labs, articles, tutorials. And everything you saw here, even the web component stuff, all compiles to JavaScript. So you can write Dart, take advantage of those great semantics, language, and tools, and still deploy across the modern web. So I think with that, I think we're all ready to go. OK. Thank you very much. Appreciate it.